the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students who are currently going through linear independence, not from somebody else, but just in linear algebra itself. In this video, we're going to focus on proving two theorems. They both were mentioned in the previous video, and I told you then you cannot use them until they're proved. And here we are, we're going to prove them here. It was just nice to kind of separate them out and prove them in a separate video. They're short proofs, so don't freak out. The first theorem says the following: a set of only one vector is linearly independent if and only if the vector is not the zero vector. If you've been watching my videos, then you know the structure of a proof for a bijection like this, an if and only if. So let's go ahead and just start right into it. And I was just about to jump into this when I realized I probably need to massage the language on this a little bit to really fit the if P then Q format and then if Q then P format, because a lot of people will not understand if I just jump into it. So here's the deal. There's a little bit of a setup here. So if I rewrite this, I can write this as follows. Here we go. So we're going to start both sides of the proof with just a statement. We have a single vector set. Then our real if and only if is the following. The set is linearly independent if and only if the vector in that set is non-zero. The first statement is P, the second statement is Q, and there's our if and only if, our bijection symbol. Going ahead and starting, let's do if P then Q. This is going to feel a little bit like a proof by contradiction. It actually sort of is. So we're going to assume that P is true. That is, suppose that our set of one vector is linearly independent. Then by definition, any linear combination of that vector equaling zero will imply that the weight on that vector must be zero. And that's just because of the definition of linear independence. Now what I'm going to do, we want to arrive at the fact that V is non-zero. Well, let's go ahead and again, we're going to argue by contradiction. We're going to suppose that V is actually zero. And this will actually run counter to one of our previous statements. So assume that V is a zero vector. Again, that's running counter to actually what we want to prove. But if you assume the negation of Q, so if we assume P and then say that therefore the negation of Q must be true, then through deductive arguments, if we arrive at a contradiction, the only assumption we will have made within our argument must be false. And our assumption right now is that V is the zero vector. So assume that V is the zero vector. Then 5, for example, times V is equal to 5 times the zero vector, because that's what V is, which is the zero vector. That is, there is a non-zero solution to x sub 1 times V is equal to 0. Now remember, V is linearly independent. So because we started not with the supposition, I mean it says suppose, but we started with the strong antecedent that V is linearly independent. That will imply the only solution to this is x sub 1 being 0. That's the only solution. Yet we assumed something and arrived at yet another solution to something times V is equal to 0. Specifically, we arrived at 5 times V is equal to 0. That contradicts linear independence. Thus, our assumption must be incorrect. Our assumption was that V is 0. If that's incorrect, well, the only other option is V is not 0. There we go. So that proves that if V, the set, is linearly independent, then V must not be 0. Now let's go the other way. And by the way, that proof was a proof by contradiction. There's really, as far as at this level, about 4 main proof styles: direct, proof by contradiction, proof by contraposition, and proof by mathematical induction. So far in this course, in these video lectures, you've seen 3 of the 4. You have not seen proof by mathematical induction in this course. However, you should have seen a lot of it in your pre-calculus course. The if Q then P I'm going to do as a direct proof. So we're going to suppose that V is non-zero. Then a random number times the vector V is just that random number times, well, the column vector v1 through vn. By scalar vector multiplication, I can bring that scalar on the inside and you have this vector right here. The only way for that vector to ever become 0 is if all of those products, all those entries are 0 identically. Now remember, V itself is not the 0 vector. So not all entries in V are 0. Let me go ahead and make that note. Where V1, V2, all the way to Vn are not all 0 simultaneously. It is okay for all of them but 1 to be 0, but it is not okay for all of them to be 0 because then that would break our antecedent. Our antecedent is that V is not 0. So that is not allowed. Therefore, all of those numbers cannot be identically 0 at the same time. Well, if you look at this then, there must be an equation in here, and let's just call it x sub 1 times v sub I is equal to 0. There we go, there's an equation, x sub 1 times v sub I equals 0 for some indexed I in that list though, where v sub I is non-zero. Thus, the only way for that equation, by the way, we're not at this point working in linear algebra. At this point, we're working with good old algebra. So if you have a product of two numbers becoming 0 by the 0 product property, either the first number is 0 or the second number is 0. However, since not all of those v's, v1 through vn, are 0, we've chosen one of them such that the v sub I is non-zero, thus that forces x sub 1 to be 0. This is logical deductive arguments. There's no flaw in this statement. So through logical deductive arguments, if we start with the fact that v is non-zero, then we move to, well, if I take some number times v, which looks like this, and I say I want that to be 0, well, that means that all those entries must be 0. So far, it's locked down, cool logic. However, because v is not identically 0, at least one of those values of v is non-zero. So let's go ahead and grab that one non-zero value of v. That equation would be x sub 1 times v sub I is equal to 0, where v sub I is non-zero. Thus, for that equation to be true, we'd need x sub 1 to be 0. Going all the way back to the beginning, for this to be 0, that means x sub 1 must be 0. That is, the equation x sub 1 v equals 0 requires x sub 1 to be 0, which is the trivial solution. So if this equation right here, which is a vector equation containing the only vector in our set, is only true with the trivial solution, then that vector is linearly independent. And there we go. That's the proof both ways. Although there's probably an easier proof. I was just making it up as I was going along, but that's a good proof. That's a decent proof of it, I guess. All right, let's see what the next one is. Now this one is interesting. And this theorem will grow. It grows into a set of many vectors. But right now it's just listed as a set of 2 vectors. So a set of 2 vectors is linearly independent if and only if the vectors are not multiples of one another. We'll start with the fact that we have a couple vectors from the same space, so both from Rn. Now this time when I write the proof, I'm not going to showcase if P then Q and then if Q then P. I'm just going to write it. If U and V are linearly independent, then the only solution to this vector equation is a trivial solution. That is, the only solution occurs when x1 is equal to x2 and they're both equal to 0. But if that's the case, let's go ahead and assume that u and v are actually multiples of each other, even though we're trying to prove that they're not. Let's just assume that they are. Then our vector u is just some scalar multiple of the vector v, just because of being the definition that they're multiples of one another. Therefore, the linear combination of 1u minus kv. Now that is actually a linear combination. Both of these are non-zero scalars, right? And if you add those two vectors up, well, remember, u is just k times v. And of course, we have a property of vectors that allows us to factor that k out. We have the additive inverse property of vectors that lets us state that v plus the opposite of v, vector that is going to be the zero vector. And we know that a scalar multiple of the zero vector is still the zero vector. That is, we have found a linear combination of u and v that turns into zero where the weights are not zero. But wait a second, u and v are linearly independent, so the only way a linear combination of them is to become zero is if both the weights are identically zero. So we must have made a bad turn somewhere, and that bad turn is the assumption statement, the contradiction statement, basically. So therefore we have to take back that assumption and go the opposite direction. The opposite of assuming that u and v are multiples of one another is the actual place where we want to arrive, which is that u and v are not multiples of each other. And that is the forward proof. Now the backwards direction, going from here to here, I'm going to prove by contraposition. So I'm going to go ahead and instead of saying if Q is true, then P is true, instead of going in that direction, I'm going to go the other direction. I'm going to say, suppose P is not true, and we're going to prove that Q is not true. Suppose that U and V are linearly dependent. We want to arrive at the fact that the vectors must be multiples of one another. Well, if U and V are linearly dependent, then there exists C1 and C2 such that C1 times U plus C2 times V must equal 0, where C1 and C2 are not both 0. Now I'm going to get rid of the weird case first. If U is equal to 0, then V has to be a multiple of U. It's just 0 times U. In that case, again, we arrive at where we want, which is that we started with a set of two linearly dependent vectors. If one of them happens to be 0, then the other one is a multiple of the other. So that takes care of that. If either of them are 0, then the other is automatically a multiple of the other. So that takes care of those two cases. Now let's talk about the situation where U and V are both not 0. Then we have this equation right here. U and V not being 0 means that U is equal to a negative C2V over C1. Remember, C1 can't be 0 because if C1 were 0, that would mean that C2 would have to be 0. And remember, we're saying they're not both 0. So that's okay. So once we get there, if U and V are both not 0, I just solve this equation up here for U, and I find out that U is actually a multiple of V. So in all cases, if we suppose that U and V are linearly dependent, then no matter what, U and V are multiples of each other, which is exactly the contrapositive. If these vectors are linearly dependent, then the vectors are multiples of each other. And there we go. That's actually the full proof. Now this video you might have to watch a few times just to get that proof, but again, I did it on the fly, so I'm sure there might be a smoother way to do it, but I have to rush off to office hours. So you guys have a wonderful day. I hope to see you in future videos. Be wonderful human beings.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much, that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.